Well, hello and welcome to this session on Maple. I'd like to present to you the work that I've done on this task of analyzing the quantum momentum rate equations and their solutions. And as a sort of intro, I'd like to explain the background to this. When I was doing my PhD thesis, I explored a different representation of quantum mechanics. Typically, one thinks of the wave function as an expression of quantum mechanics, and the Schrödinger equation actually defines the dynamics of the wave equation. But it's possible to represent quantum mechanics in a different way, and in this case, we represent the quantum mechanics in terms of the real momentum and the imaginary momentum. And perhaps those of you who've got some familiarity with quantum mechanics will recognize that you can express the quantum beebles, as they were, the real and imaginary momenta, in terms of the operator multiplying momentum operator on multiplying the Schrödinger wave equation, but then dividing that by the wave equation, the wave function itself. And the result of that is you get an imaginary number, which has a real and imaginary number, has those two parts, the real part and the imaginary part. And so one ends up with what the so-called momentum beebles, the real one and the imaginary one. And one can investigate the dynamics of those beebles by turning the Schrödinger equation into a pair of coupled partial differential equations in the momenta. And it was something that I raised in the thesis and didn't follow through on. And recent months I've taken up the baton to try and work through this one. So anyway, you can see here, we explicitly scale. The idea is that we're looking at the behavior of classical mechanics and quantum mechanics, and looking at the behavior of the momentum fields when they're classical and when they're quantum, and also in the range between. And typically, what happens is that in that range, you have a scalar, which we called h bar, which multiplies Planck's constant. And when that is 0, it's classical. When it's 1, it's quantum. And so you've got this range from 0 to 1 in this unitless number h bar. In front of you now on the screen, you can see that we've got laid out the two equations that are derived in the way that I explained in the intro. So we have the real momentum equation, which is the first one there, number 1. And at number 2, we have the imaginary momentum equation. And you'll notice that the imaginary momentum appears in the real momentum equation and vice versa. So these equations are coupled together. And the task we have is to examine solutions of these coupled equations. And we observe that we're setting h in the PDU equation. You've set h bar equal to 0, and that scales out the diffusion term and the self-advection term, known as the quantum potential derivative, actually, in the Bohm interpretation of quantum mechanics. And the second equation doesn't have a factor of h bar in that equation. So whereas h bar does occur in the first equation for u, and that's an important feature. Now the question is, how do we solve this? Well, we make use of PD-solve, Maple's partial differential equations solver, and we actually have to set up the boundary conditions for that, and you can see IBCU and IBCV, the two types of momentum, and you'll notice that there's not just values of initial conditions and boundary conditions. We've also got the derivatives there, the d1s and d of u and v, expressed as those derivative boundary conditions, because we have second order derivatives in the two equations above. And then we join them together as the IBC, a union of the initial and the boundary conditions. And we set this theta value, theta v, which I'll describe to you in a minute. Theta v defines, theta val, sorry, defines the integration algorithm. And it can go from naught all the way up to to 1. And at one end, it's explicit integration, and at the other end, it's implicit. And you can then solve the equation. And as you saw on screen there, you get solutions as expressed there. And you can see there the dynamics of those solutions. Here, in this case, this has got a value of h, which is, if you look above the diagram, of 0.25, which is pretty classical. And you saw the red one, the red momentum solution. Recall that the force on the real momentum is twice that of the force on the imaginary momentum. And so that was one example of a solution to the equations. We've run solutions for these equations in the domain of h bar and theta v. Now let's go back and remind ourselves, h bar ranges from 0 to 1, which is a scaling of Planck's constant, and theta v, again, here there's an integration parameter. I'll reiterate that it ranges from 0 to 1 too, but we found here in this table, which you can see, that the run times for theta v up to about 0.45 and even 0.48 were very low indeed, when the expected transient length time is actually set to 40. So in what goes on in this hereafter in this in the worksheet is that we assume that we're going to explore the region of theta v from 0.5 up to 1. And we will explore the whole range of h bar from 0, classical that is, all the way up to quantum mechanics as 1. So that's what this table is showing. And this is the sort of thing one needs to do, is to establish the viable domains when you've got a pair of PDEs like this and parameters that are controlling them. You may not get solutions. This could be because for physical reasons, that the physics does not allow it, or it could be because of numerics or whatever. But anyway, this chart obviously shows pretty consistent low numbers in terms of run times there, which are the 2.44 second minutes, and 40, another much higher. The end point is at 40. The run time, should I say, is at 40. So here we have an example of some transients. These files are created as demonstrated above, and you see they're running at the plot 1 as it's labeled. Theta v is 0.5 and h bar is 0.5. And we compare that with plot 2, where theta v, the integration parameter, is now set to 0.1. And you can see how much smoother on that plot 2 is compared to plot 1, where they're much more implicit integration algorithms. It smooths out the solutions. And this is for an h bar value. This is a semi-classical value of h bar, which is 0.5, middle of the range from the physics standpoint. But numerically, we start in the middle of the range with that one. Well, that's the only one we can start with, because we've decided we can only work with theta v's greater than 0.5. And plot 2, you can see that is much, that I've just labeled there, that's plot 1, and see the variations. Whereas in plot 2, you've got these smooth curves, and that's as a result of the integration scheme. So here you've got the integration scheme interfering with the physics, we might argue. How do you strike that balance? And then plot 3 and plot 2 are comparing what happens when you've got the same integration algorithm. Here theta v is 1, but we change h bar. We're at different points in the semi-classical domain, h bar 0.5 and h bar 0.75. So, where we and in this range, should I make an explanation below that? See, in the 0.5 to theta v is 1, and we have semi-explicit to implicit numerical integration schemes I've pointed out, and that's ranges through the semi-classical regime in plots 2 and 3. So we see the smoothing effect. I'm reiterating what I've described to you, but it's worth reading it again. Smoothing effects of the theta v numerical scheme and the physical transition from classical through to semi-classical and quantum as h bar increases from 0 to 1. We've demonstrated here 2 particular values of h bar, which is the physical parameter. And you can see there on the right the dynamics of that particular solution being demonstrated with the slider on the top left where it says current frame 50. So we run it from 0 to 40 seconds in each case of all of these files. For each parameter set, theta v and h bar in the table that we're showing above. So that's the end of that. A little bit of a section there. Now then, what we want to do now is to investigate, plot the file entropy of the solution files as a function of h bar. As you move through the classical to the quantum regime, you want to look at how the run files are behaving. Are they completing? Are the run files completing? Do they have a very small size, or they haven't run, or they've collapsed? And so what we do there, we are expressing there is the constraint, the dynamics effectively of the solutions you're finding in this h bar range. And you can see there that each of those dots is a file, and it's entropy as a function. So the entropy of a file is expressed as the gzipped file size over the un-gzipped file size. That gives you a measure of the entropy content. And you can see that you've got a very obvious transition of behavior at 0.5, h bar is 0.5. And there's a lot of erratic behavior in the classical regime, specifically as you get very, very close to h bar equals 0. And then in the quantum regime, it's fairly steady. We seem to have settled down there. And this is with theta v integrating the implicit at 0.8. So these are fairly smooth transients. Here's an example here of the run times of the same result. Here you can see that these files simply don't get anywhere near the end time, which is 40. And so there's a complete gap there. Why won't these solutions work? Why is that the case? And then once you get to 0.5, you start to get full run times. So that's an interesting question, and one needs to answer, and I'm trying to understand. If anyone has any ideas, please let me know. And here's another plot, which is instead of runtime, it's file size. And naturally, file size would be small if these solutions are stopping prematurely. And you see the same trend, and you see the same trending in the quantum regime, and yet you see no results in the classical regime. And here's the entropy plot. For the case of the multiplier theta v equals 0.5, the lowest possible we can run with theta v to get in getting solutions. And you actually are seeing here all those results that were along the bottom here. We actually measure what their entropies were, and you see it's fairly chaotic range of entropies in that region there. And on the right-hand side, you see trends, which is really much more in the quantum regime. You can take out the sessions that the runs that actually didn't complete, and you're left with that trend. The quantum end of the works in green, and also right up against the classical at the far end. So this is so these results, these graphs are very useful for actually expressing some sort of difference in behavior between classical mechanics and quantum mechanics. The big question is, why does it happen at 0.5? That I haven't really found an answer to. Whereas I've some more plots here of run times as a function of the H multiplier, which I think we've seen before, actually. Worth looking at again, I suppose. And here we are, similarly for the solution runtimes with the colors in. That's cosmetic, really. And here's the file size one. You can see the file sizes here on the left-hand side. These are raw file sizes. You've got megabytes, a few megabytes the size than the runtime files. And here is the scatter in the entropy, which I've shown already. We move on down eventually to the bottom. And so I hope this has given you an indication of what I'm trying to set out to do, but also to showing how useful Maple is in projecting the results of these solutions, and also you know how you actually successfully solve with a pair of coupled PDEs. As we go down further, I think, in this presentation, we have, and that comes to the end, that finishes. Thank you for listening. Oh yes, so here I am back on screen now. So my closing remarks are that this has been an interesting project, and it's actually enlightened me, or at least opened up an avenue of questions which I need to try and get answers to. You know, why do we get those transitions, particularly happening at halfway through that semi-classical domain? And there's nothing in the equations, as far as I can see, that actually prescribes that it should do that. So that I imagine it's something to do with the physics. Anyway, if there are any more questions and answers that you would like to have, then I look forward to discussing with you in the question and answer session. So I'm going to just close now and shut down from there. Thank you for listening.